Symmetry of functions. There are different types of symmetry that can exist between relations or functions and their graph. The first one is symmetry over the x-axis, and a relation has symmetry over the x-axis when f of x is equal to negative f of x. And we're saying that it's a relation instead of function in this case because the same x value will produce two different y values, making this relation not a function. And this relation is that x is equal to y squared. If you elected to solve it for y, you would square root both sides. And because you're solving, you would need the plus or minus in front. So it would be y is equal to plus or minus the square root of x. So if you were graphing y equals plus or minus the square root of x, you would get this relation, which again is not a function. A function has symmetry over the y-axis when f of negative x equals f of x. So in the absolute value function, or in a regular parabola, y equals x squared, you will have symmetry across the y-axis because the two different x values give you the same exact y value. They are symmetrical about the y-axis. A function has diagonal symmetry over the line y equals x when the function is the same after the x and y points are changed. So for example, when y is equal to 1 over x, we have the point 1, 1. And when you switch those coordinates around, you will get the same exact point. This point right here is 2, 1/2. And if you switch those around, you get this point, 1/2, 2. And the same holds true in quadrant 3, or with the negative values. A function has rotational symmetry about the origin when f of negative x is equal to the negative f of x. Or when you substitute the negative in, you get the negative of the original output. So for example, when we have 1, 1 as our first point, if we take negative 1, where this f of x is equal to x to the third, when we substitute negative 1 in for x, we get negative 1 to the third power. And when we evaluate it, it's negative 1. That would have been the same thing if we would have just taken this point, 1, 1, and put the negative 1 in for x, and then just switch the sign of the y coordinate. And that does hold true. The types of symmetry that will be emphasized the most in this course are the y-axis and the origin symmetry because they yield functions always. Now let's talk about how symmetries are related to the type of functions that we have. An even function has line symmetry about the y-axis. This occurs when all of the terms in the polynomial contain even exponents. So in this example, we have y is equal to x squared minus 4. You could also rewrite this as y equals x squared minus 4 times x to the 0 power, because x to the 0 power will be 1, and 4 times 1 is 4. So it would simplify to x squared minus 4. So remember to examine the degrees of all terms, including the constants. They have that degree of 0, and 0 is an even number. When identifying symmetry, if a function is an even function that is symmetrical about the y-axis, then f of negative x is going to equal f of x, meaning whether you substitute in the negative x value or the positive x value, they will both yield the same output. So here's an example. If we are given this even function, f of x equals x squared plus 5, if we substitute negative x in for x, we end up getting negative x quantity squared. And when you square both the negative 1 that's out in front and the x, you would get negative 1 squared times x squared. Well, negative 1 to the second power is positive 1. So you're just left with x squared plus 5. So therefore, f of negative x is equal to x squared plus 5, which is the same original function. So we can see that f of negative x and f of x are indeed equivalent to one another. And this property, f of negative x being equal to f of x being true, tells us that f of x is symmetrical over the y-axis, as we would expect with this even function. It is important to note that all functions with even exponents are not necessarily even functions. Here's an example that has even exponents, but it is not an even function. We're given this function f of x, and that is equal to x plus 5 quantity squared. If we substitute negative x in for x, we get negative x plus 5 quantity squared. Well, you can't distribute the square to both terms. That is a common mistake that some people make, because there's an addition sign in between here. It's not multiplication. What this actually means is negative x plus 5 times negative x plus 5. And if we go through and use the distributive property multiple times, or when it's two binomials, you may also know it as FOIL, but again, that only occurs when you have two binomials, we will end up getting a positive x squared, but then we'll have minus 5x minus another 5x, so that'll be minus 10x, and then plus 25. Notice in this form of the function, we don't have all even exponents, we have an odd exponent in our trinomial. Therefore, it is not an even function. And this negative x plus 5 quantity squared could also be written as 5 minus x quantity squared. And again, if you rewrite it as 5 minus x times 5 minus x, you will get x squared minus 10x plus 25. And since not all three terms in our trinomial are to an even exponent, it is not considered an even function and is therefore not symmetrical over the y-axis. It's also important to note that f of x, which is x plus 5 squared, and f of negative x, which is 5 minus x squared, are not equal to one another. And again, this is happening because these functions are not even. Now let's go over odd functions. An odd function is symmetrical with respect to the origin, and this occurs when all of the terms of the polynomial contain odd exponents. For example, y equals x cubed. Remember to examine the degrees of all of the terms. In this case, we only have one term, and it is raised to an odd exponent, so it is indeed odd. If the function is an odd function that is symmetrical about the origin, then f of negative x will be the same as the negative of the function f of x. So here's an example. If we're given the odd function f of x is equal to x cubed, let's substitute negative x in for x. So that would be negative x quantity to the third. And remember, this can be rewritten as negative 1 times x raised to the third power. And when you have multiplication between two terms, you need to bring the third power to both of your terms. So that will be equivalent to negative 1 raised to the third power times x raised to the third power. Well, negative 1 to the third power is negative 1. And then x cubed is x cubed. And you don't necessarily have to write the entire negative 1. You could just leave it as negative x cubed. So that's how you would simplify f of negative x. Well, couldn't I have also gotten negative x cubed by just sticking a negative right in front of the original x cubed? Yes. Therefore, f of negative x is equal to negative f of x. Therefore, the function is symmetrical about the origin, as we would expect for an odd function that contains only odd exponents. It is important to note that all functions with odd exponents are not necessarily odd functions. Here's an example of a function that has odd exponents, but we'll see how it is not an odd function. If we substitute negative x in for x in our original f of x function, we end up getting that f of negative x is equal to negative x minus 2 quantity raised to the third power. We know that we can factor out a negative 1 from both of these terms. And when we do that, we end up with x plus 2, and then the entire thing is still raised to the third power. Now when we have two terms inside of grouping symbols or parentheses, and they are separated by the operation of multiplication, we can distribute the exponent through to both terms. So we have negative 1 raised to the third power times x plus 2 raised to the third power. And when we evaluate negative 1 to the third, we're left with negative 1 or a negative sign out in front. And then we still have x plus 2 raised to the third power. Now if we look at negative f of x, that's going to be equal to negative, and then f of x is x minus 2 raised to the third power. Notice f of negative x and negative f of x are not equal to one another. Therefore, it is not symmetrical about the origin, as we would expect with only seeing an odd exponent in our function. Another way to show that this is not an odd function would be to expand both f of negative x and negative f of x. F of negative x can be rewritten when expanded as negative x to the third minus 6x to the second minus 12x minus 8. And then if we expand out negative f of x, we end up having negative x to the third plus 6x squared minus 12x plus 8. And we can see that these two functions are not the same. And when expanded out, they have both odd and even exponents, which also makes it not an odd function. Now let's discuss the graphs of functions. When studying the graphs of functions, scientists like to analyze many different aspects of the graph. By the end of this course, you will also be able to analyze various functions and determine the criteria found below. Ones emphasized in this unit are the domain, range, intercepts, x and y intercepts that is, and whether functions are even, odd, or neither. Depending on the function, you may or may not have minima or minimum values, or maxima or maximum values. You could also have functions that are increasing, decreasing, and a little bit of both. And you'll also be talking about end behavior. Again, those are only as you continue through the course, and the concepts that have been covered thus far are domain, range, intercepts, and whether functions are odd, even, or neither.